Hey everybody, in this video I'll be giving an introduction to deep learning, which, as many of you already probably know, has become a very prevalent topic in recent years. We'll be going over what deep learning is, the structure behind AI models that use deep learning, and the theory behind training these models so they could accurately predict the outcomes of whatever situation we want to model. So let's just get straight into it. And let's first define what deep learning is. And to do that, let's first actually go over how we would typically solve different programming problems, right? Let's say we wanted to determine which of two numbers, x0 or x1, is greater. To do that, we would simply use conditional statements in our program. If x0 is greater than x1, then we'll give one output. Otherwise, we'll give a different output, right? Depends simply on which one's greater. We're following this rule-based system that we defined in our program. And then once we have our program, we could, of course, just compile it and run it. And this is a very valid solution in a lot of cases. In fact, if we can do this, then we should do this, right? If we give the rules and it works every time, then this is a perfectly valid solution. However, sometimes we have situations with rules that are extremely complex and not really well defined to us. So, this is where machine learning really comes in handy. The whole idea behind machine learning is that we don't actually explicitly tell the program that we're writing the rules that it should follow. Instead, we're going to be training the program to identify some sort of correlation between the inputs we give it and the expected outputs, right? Now, deep learning is just simply a subset of machine learning that relies on neural networks. And the whole idea behind neural networks is that it's supposed to try and mimic the structure of the human brain, has layers of connected neurons, and we'll go over the structure of neural networks in a bit. But essentially, as we said, neural networks are given some training data, and over time, after iterating through the training data, it'll eventually, hopefully, be able to find the rules or the correlation between the inputs and outputs, and then we could use this trained model to predict the outputs of new inputs that we didn't use in our training data. So now that we understand the basic idea behind deep learning, let's now go over the structure of neural networks. And to do that, we first need to understand the basic structure of neurons. As we said, neural networks are made up of many individual neurons. Now, there's many different types of neurons, but the type that we'll be covering specifically in this video is the perceptron. And this is the simplest type of neuron. Now here is a visual diagram of all the elements that make up a perceptron, and we'll go through them one by one. We first have a set of inputs that we give to the perceptron. We can define ourselves how many inputs we want to give to the perceptron. However, these inputs have to be numerical. So it's important that whatever training data and testing data that we use is converted into some sort of numerical form. Now, for every input that we give, we will have a corresponding weight. Now, the weights are just numbers. These numbers are initially random, but as we'll see later when the model is trained, these weights will be adjusted. So again, for each input, we have a corresponding weight. And then we take a sum. The sum of the product of each input and its corresponding weight. So x0 times weight 0, x1 times weight 1, and so on. We add all those products together. And then we add a bias to that sum. And a bias is just another initially random number, which will later be adjusted when we train the model. And then, finally, we apply a nonlinear activation function to our sum. Now this function we can choose, and ultimately it's up to us to decide what function we should use to best model the situation. But the whole point of a nonlinear function is just to allow us to model more complex situations. And then whatever returned from that function will be the output of our perceptron. This is what a perceptron will look like mathematically. It's just what I said, the sum of the inputs times the weights plus a bias, and a nonlinear activation function applied onto that sum. Now, again, when it comes to nonlinear activation functions, there's many different functions we could use, and it's up to us to choose which one would be best for our situation. Some common examples are the sigmoid function, which is good because it gives us a value from 0 to 1. We could use the hyperbolic tangent function, or we could use the rectified linear unit function. And again, there's many that we could choose from. These are just a few examples. Here's an example of a perceptron. As you can see, this one has 3 inputs, and it uses the sigmoid function as the nonlinear activation function. So now that we covered an individual neuron, let's go over neural networks as a whole. So when we're going to be looking at neural networks visually, to make things simpler for us, we'll simplify the visual diagram of neurons to only show the inputs and the outputs. We're not going to show all the other elements that make it up. So in neural networks, they're made up of layers of neurons. We can see here, this is a single layer made up of 3 neurons. And the important thing to keep in mind when we create neural networks with perceptrons specifically is that every input going into a layer must be connected to each neuron within the layer. So we can see here we have 4 inputs, and all 4 inputs are connected to every single neuron. And like we discussed, each neuron will have 1 output. So in this case, there will be 3 outputs from the layer. Now another important thing, just to keep in mind, again, all the inputs for each neuron are the same. However, the weights for each neuron are distinct from one another. They'll have their own weights. But for each neuron, the nonlinear activation function will be the same. That's just a rule we have to follow when working with perceptrons. So in one layer, all neurons might have the sigmoid function or the ReLU function, whatever we choose for that layer. Now here we could see an example with multiple layers, right? Here we have a total of 3 layers. The first layer has 3 neurons, second layer has 5, last one has 2. And we can see visually here how each of the layers are connected. So we see that the output from one layer, the first layer, is used as the inputs for the second layer. And the outputs from the second layer are used as the inputs for the third layer. And this is just an important thing to recognize. For any layer we have of neurons, the amount of inputs that it has must be equal to the number of neurons in the previous layer, since each neuron gives specifically 1 output. Now this is just an example of a simple neural network. This might look visually complex, but relatively this is quite simple to what complex AI models would use. And this is actually the neural network that we'll be using in a future video when we discuss coding AI models. And this neural network we can see is made up of 3 layers. The first 2 have 8 neurons, and the last one has 2 neurons. And The goal we have in mind, the problem that we want to solve using this neural network, will be to distinguish which of two inputted numbers is greater. Now, again, I mentioned at the beginning that we, of course, could solve this problem very simply just using conditional statements. However, this is just a learning experience, if you will, just to show how we can use neural networks to solve different problems and how we can train models. So now, up to this point, we technically can create our own neural networks. We understand the structure. Technically, the concept is relatively simple. We're just creating layers of neurons and connecting them to each other. Now, of course, it can get quite complex with potentially billions of neurons. However, it's enough. Now, if we were to simply just create a model and we were to give it a set of inputs like we have here in this example, 1, 5, and 4, do we think that it would give the output that we expect? Well, of course not, right? As we said in the beginning, the weights and the biases of all the neurons are completely random. So even though, for this example, we might expect an output of 1 for the given input, we might get some completely random number that's quite inaccurate. So then, how do we train our model? Again, training is a very big concept that we mentioned earlier, but how do we train our model such that it can accurately predict outcomes? And the first step to doing that is identifying just how inaccurate our model is. We want to see how off we were from the expected outcomes, right? So let's say we have an input, xi, and an input in this case is just 3 numbers. We have then a predicted value and an expected value, right? The predicted value is what our neural network spits out, and the expected value is what we would like our neural network to output. And to see just how off we were, the predicted and expected values were, we can use what is called a loss function. And a loss function is just simply a mathematical function which takes as an input our predicted and expected values and compares the two and returns in some numerical form our inaccuracy, if you will, our loss, so to speak. Now, if you were to think for a second, what could we use potentially as a loss function? You might think, well, why don't we just take the difference between our predicted value and our expected value? And this is a very valid approach. This is actually what will lead to the simplest type of loss function, right? Now, one more thing we have to add to this is we can't have a negative loss. So we simply take the absolute value of the difference. But so far, up to this point, what we just need to understand is that in order to test the accuracy and inaccuracy, rather, of our neural network, we can simply use a loss function. Now let's talk about this concept of empirical loss. The loss function we just looked at was used for a single input, right? But when we're training our models, we're not using a single training input and output. We have an entire data set. So the empirical loss, simply put, is just the average error our model has given a specific training set. So mathematically, what we do is we just apply our loss function to our entire set of inputs. So here in this example, we have inputs x0, x1, x2, and so on, where each input, again, is just 3 numbers to represent x subscript 0, x subscript 1, and x subscript 2. And we apply the loss function to every input, and we take the average of those losses. And that's just simply our empirical loss. Now, earlier we mentioned one type of loss function that we could use. It was taking just the difference between the predicted and expected value, and applying the absolute value function to that. And that is the simplest type of loss function we could use. This is called mean absolute error, or MAE for short. And just, as we said, simply takes the difference between the predicted and expected values and applies an absolute value, and takes the average for the entire data set. Now, there are other types of loss functions. In fact, there are many. Another type of loss function would be mean squared error. This is quite similar to the previous function we just talked about. It's a very commonly used function. The good thing about this function is that this will penalize larger errors more rather than smaller ones. And as you can see, mathematically, all we do is, instead of applying absolute value, we now square the difference. One more commonly used type of loss function is the binary cross entropy loss function. And this is especially useful when we want an output that's between 0 and 1, such as a probability. Now, of course, there are many different types of loss functions, and it's up to us to choose which loss function would be best for our situation. So we now understand how we can measure the inaccuracy of our model using a loss function. Now, of course, we want to make our model as accurate as possible. That is, we want to lower the loss as much as possible, given the weights of our model and the training data that we give it. So here, I just have a loss function shown graphically. This isn't necessarily a loss function we would actually use, but it's just for demonstration's sake. And this loss function is being applied to a single weight. Of course, normally it would be applied for multiple, but again, this is just to make a point. Now, the loss function, what does it take as inputs, as variables? It takes, of course, as I said, the weights of our model and whatever training data we give it. Now, of course, we're not actually going to be changing the training data. So the only variable values that we're going to be changing is the weights of the model. And this is a very important point, just to highlight, that what actually defines our model are these weights, these numbers that are initially random, that are going to be applied to our inputs that we give it. And once our model is trained, these weights should be adjusted such that they give an accurate output. So, when it comes to training our model, we want to modify these weights such that we lower the loss as much as possible. So graphically, that means bringing our loss, or choosing a weight that brings our loss to the minimum of the graph. Right here. And now how do we do that? Well, we'll be using a process called gradient descent. And this is a very key part of training our model. So what is gradient descent? Well, essentially, we will be calculating the derivative of our loss function in relation to each weight. In this first example, we just have a single weight. Now, this derivative, or partial derivative, we actually refer to as a gradient, hence the name gradient descent. Based on the gradient, specifically the sign of the gradient, we now know which direction we should modify the weight in order to increase or decrease the value on the y-axis, or loss. And of course, we want to decrease the loss. So again, based on our gradient, we can see now in what direction we should modify our weight in order to decrease the loss. And then we'll do exactly that. We'll multiply the gradient in relation to our weight by a small increment, and then we'll subtract that from the current value of our weight. Now this small increment we refer to as the learning rate, and we'll touch more on its importance later, but essentially defines how fast and aggressively our model will adjust the weights. And of course, again, we multiply that with the gradient that we calculate. So now we can see this process in action graphically. So we can see the black dot is where on the graph of the loss function is where our loss is currently at. And then based on the calculation, we see that this calculation that we just described with the gradient and multiplying it with the learning rate and subtracting it from our current weight, it tells us now we need to move our weight slightly to the left. And we see that does in fact decrease our loss. So if we do that, we can then repeat the process. And then it tells us, okay, we need to move it slightly more to the left. And we can see that does in fact decrease our loss. And simply put, we can just keep on repeating this process until eventually we should converge onto the minimum of the graph. Now, of course, it's not that simple, right? We don't have a single weight. We have to calculate the gradients for potentially thousands to millions to even billions of weights. However, mathematically, it's still the same thing. We're just adjusting the weights every time such that we decrease the loss. We move down the graph, if you will. So this is just another graphical example if we were to have two weights. Of course, once we get more than two weights, it becomes a lot harder to visually represent, but we just have weight 1, weight 2, and the vertical axis will show our loss. So if we were to start on some random point on this graph, we would calculate the gradients for both the weights, and that would tell us how to adjust the weights to move down this graph. Again, eventually we would converge to the minimum of this graph, ideally. So now we'll be touching more on the value of our learning rate. But before that, I just want to reiterate the process of gradient descent because it's essentially how our model is being trained, right? So once again, in gradient descent, we simply take the partial derivative of the loss function in relation to every weight. We call these partial derivatives gradients. And now based on the sign of each of the gradients, we can determine the direction that we need to adjust our weights in order to minimize the loss. And then we, of course, adjust the weights in those directions by some small increment. And that is determined by our learning rate. Now, it's important that we pick an effective learning rate. We can see that if it's too high, graphically, then our adjustments would cause us to bounce all over the graph, right? Like so. And we might not even reach the minimum. We might jump over it, completely ignore it. The point is, if the learning rate is too high, we might over-adjust or overcorrect too harshly. In fact, if it's too high, we might even just bounce from one place to another repeatedly and never reach the minimum. And this is exemplified even more by the fact that the graph of a loss function would never be this simple. In fact, they would be extremely complex, and the chance of this happening, if the learning rate is too high, the chance of us missing the minimum would be extremely high. Alternatively, it's also an issue if the learning rate is too small. We may still be able to converge to the minimum. However, we would do so at an extremely slow rate. And as you can guess, the process of training a model is extremely computationally intense. So we want to be as efficient as possible, right? Not only that, but again, the loss graphs are extremely complex, and with a slow learning rate, it's totally possible to get stuck into false local minimum and not reach the true minimum. So we want a learning rate something like this, where we're not too slow, but we're not over adjusting too much. Now, how do we decide what our learning rate should be? Well, one option would just be to simply try different learning rates and see what works. And this is a valid approach, and in some cases, we already know what are good learning rates that can work for specific situations. Or, instead, we could use an adaptive learning rate, which changes based on the values of our gradients. And for that, as we'll see in a future video when we talk about the programming AI models, we can simply use an optimizer. And optimizers are just these algorithms that we can implement, and part of their function is to set an adaptive learning rate. And of course, there are many optimizers, and we just have to choose one that we want for our situation. A very common one that's listed here is Atom, and that's quite a good optimizer. So now we basically covered all the puzzle pieces that are necessary in order to train our models. However, we didn't actually specify how we calculate the gradients in gradient descent. Now, this process of calculating the gradients is known as back propagation. And we'll go over with a simple example how this is done. So let's say we have some neural network, and we want to look specifically at the gradient of these two weights shown graphically, W1 and W2. We see that they're connected, very straightforward, one in front of each other, and the output from the final neuron we assume is applied to some loss function. Now we want to calculate the partial derivative of this loss function in relation to W2 and W1. So let's start with W2 first. We see that the loss function L, our loss function L, is dependent on the value of that is outputted by our neuron F2. That in and of itself is just a function of W2. So we see we have a function within a function. Here we can use the chain rule from calculus to get this. This is how we calculate the gradient of the loss function in respect to W2, right? Which is a simple application of the chain rule. Now what if we wanted to do it for W1? Well, let's replace W1 in this equation. And we notice that, again, for F2, it's dependent on the value outputted by the neuron F1, since we're now looking at in the context of weight 1. And we know that the neuron F1, what it outputs is just a function, some function, of the weight 1, W1. So again, we have a function within a function. So we can simply apply the chain rule again. And now we get the gradient of the loss in respect to W1. So this is essentially how we can calculate the gradient for any weight. That's why it's called back propagation. We're propagating backwards through our neural network, iterating the chain rule over and over again until we find the partial derivative in respect to every weight. Now, as you could probably guess, this can become a very tedious and complex process given a complex neural network with many weights. However, we don't actually have to worry about this ourselves. Fortunately, as we'll see in a future video when we start programming, the libraries that we use can pretty much take care of this process for us, but it's still interesting to look at. So we've now covered all the pieces necessary to train our model. So let's put it all together and see how we actually do that. So we first start with our training data, we pass it through our neural network, and we make a set of predictions based on the training data. Now, of course, these predictions are they're going to be random because our weights are random. So then we use a loss function to see how inaccurate our model currently is. Then we calculate the gradients of the loss function in relation to every weight. We do that using back propagation, of course, and then this tells us how we need to update the weights in order to minimize the loss. And then we keep on repeating this process with the same training data until eventually the loss should converge to a minimum. At that point, our model has effectively been trained. Remember, our model is just defined by the set of weights and biases. So now, if we wanted to use this model practically, we can then simply input some new testing data that we have not trained with before into the trained model, and hopefully this should give us an accurate output. So now we've pretty much covered everything in the video. Let's just recap what we covered. We've first covered the idea behind deep learning. Again, we're not defining strict rules with how our program should approach a problem. Instead, we're letting a neural network figure out the correlation between the set of inputs and outputs. We looked at the structure of a perceptron, and then we saw how they could be assembled into layers and layers in neural networks. We then saw how we could check the accuracy of a neural network using a loss function, and then how we could improve the accuracy using gradient descent. And that's pretty much it. That ends the video on the intro to deep learning. In the next video, we'll be going over a simple program using PyTorch, and we'll show how you can actually make your own AI models. And I'll see you in the next video. Thank you for watching.